All right, so welcome everyone. I'm really delighted to be hosting today Chris Lattner for one of these really interesting Ask Me Anything sessions. I think Chris needs no introduction to the programming language community, as he's the author of several high-impact projects, including the llvm Clang compiler infrastructure, the Swift programming language, and the ML IR framework. So I'm looking forward to the next half an hour. We already have lots of questions on the Slack channel. Let me just remind everyone that if you'd like to ask a question, you should go to the Slack channel, select the thread associated with this session, and ask your questions. So, right, you can ask anything. So, so we already have, so several people have already asked a number of questions, before the session has started. So I'm going to start with one of those questions.
Sure.
And I think you're a good person to ask this question from Brian Tennant from UC Santa Barbara. So he's asking, what are some important lessons that you think the industry PL compiler community could learn from the academic one and vice versa? And I think you're in a good position to answer this because you've straddled both academia and industry in your career. So
yeah, I think that I see opportunities and challenges with both. So the academic community has a lot more intellectual freedom, the ability to explore things that are not immediately commercially pressing, things like that. I think that the industrial world has a lot of concrete problems that are useful to figure out. One of the things that I think is useful is to get that interchange going. And I think internships are a really great way to do that, for example. It's interesting to me. I look at what is that frontier? What is that next set of problems that people are struggling with but are not able to kind of break through? And so you can see this when you see a lot of academic work like fermenting, and there's like a lot of papers tackling little pieces of it, but there's no unifying theory. Mm-hmm. And so I think that you can look to academia, which is publishing a lot. You can also look to industry, where a lot of the times you'll see the same thing happening, where there's all these AI chip startups, for example, and everybody's trying to make a chip, and they forget that software is the hard part. Compilers are the hard part, and so there's a lot of problems to go around. And I think that there's just pros and cons of both. They're different.
Right, thanks a lot. And so I guess the next question I'll select, which is somehow related to this one, is from Jean Zhu at University of Rochester, who asks, when developing a research prototype, especially a large one like llvm, and I guess this is something that you also had to go through while a PhD student at UIUC, there could be a gigantic gap between meeting the minimum requirements of publishing a paper and being friendly for the other researchers to adopt. So between, just publishing a paper and also having your prototype adopted. So do you have any advice for grad students on how much effort should be put to make the prototype as robust as possible? And sure. I was wondering from my side, if you can perhaps interject with some of the history of llvm and tell us how have you decided to go beyond just the research paper?
Yeah. So I mean, I think that I can't speak to what the right answer is. I'll share my experience. When I was working my way through my PhD at Illinois, when I first joined Illinois, I was planning on doing a master's and doing a non-thesis master's and getting out as quickly as possible. That was my original plan. Vikram and others tricked me into staying for 5 years and seeing it all the way through. But the way he tricked me into it was by making a lot of fun. Right? And honestly, I was having a lot of fun building things, learning things. It was a period of great growth for me. I mean, I learned so much from him and from other people around in the research group and other professors. And so my trajectory through that was a little bit unusual, I guess, because I was mostly focused on building things. I was enjoying that. And we had some friendly tension between Vikram, my advisor, and I on publish more papers, but it's not done yet. Publish more papers. Like, oh, but it only runs the benchmarks. Like it needs to be more robust, right? And so that kind of tension that we had. And I don't think that necessarily either of us was right. I think that there's a happy medium somewhere in between. And so I don't think there's one right answer for everybody. If your goal is to build a big open source community and you want to have a lot of users and you want to have other people build their research on top of your thing, then biasing more towards building stable, closer to production software, I think is good. But if your goal is to have impact on research and become aligned with the academic track, because I went into the industrial track. If you stay in the academic track and try to get a postdoc or professorship position, then I think that focusing on publication is probably the better way to go. But that's based on sample size of one, so I don't know if that's definitive, of course.
No, sure, but thanks for the answer. So I'm going to go next and ask a question from that comes from my own research group, from Michael Marcosi at Imperial College London. So, and this is something that I'm also interested in hearing what your opinion is. So, what do you think about compiler testing? So, I'm talking here about techniques such as CSmith or EMI, as well as others. So, how useful have you found this, while developing compilers? And also, how do you find the bugs reported by these compiler testing or compiler fuzzing techniques compared to the ones that are reported by developers?
Sure. So testing is one of the most important parts of compiler development. It's one of those things that a lot of people completely neglect. When I was going through school, nobody was really talking about it in academia in a serious way. The theory was you just implement the paper and it works, right? Now, in reality, things are a lot more complicated. When you start talking about multi-targeting, you start talking about things like llvm, where you have modular optimizers that can be mixed in different ways. A lot of bugs won't manifest until the conditions are right? And so even if you build a tremendous amount of code and you believe it works empirically, you're still not going to find undefined behaviors and many of the other things. So I really love the new work that's happening in even last 3, 4, 5 years, focusing on fuzzing, theorem proving, bringing more analytical techniques to the fold. And I think they're really great because they find a different class of bug that is often more nefarious and more expensive to track down if you encounter it in the wild. And so I think that that's a really great complement to writing test cases and kind of the traditional way of doing software development. And so I think they're great tools. Now you bring the question of how good are the test cases they produce, right? Well, that's a very tool specific thing. And that's where I think that there's still open work that could be done in terms of test case reduction. A lot of the work on C-reduce and things like that have helped with some of these pieces. But the closer you get down to the abstraction that the optimization or the code generator is using, the finer you can reduce it, right? Mm-hmm. Because if you're going through many layers of abstraction to get to where the bug manifests, you have to make sure that nothing between the input and the bug permutes things in a way that breaks. And so that's where I think that there's a lot more work that could be done on generating IRs directly, generating low-level intermediate data structures and things like that that could be interesting to look at. But right. I'm a huge fan of the work. I think it has really helped move the compiler technology forward by making it actually work, and that is quite important.
Yeah, I agree, and it's great to hear that coming from you as well. So just curious in terms of like bugs reported by developers. I mean, I guess they have the advantage of having occurred in the wild, but do you also see disadvantages in this kind of reports, or perhaps they are harder to debug or to pin down, or?
Well, I mean, I think that it really depends on the quality of the bug report. And if it's, some C file that's 50,000 lines of code and it says somewhere within it lies a bug, most people are not going to look at it, right? And I think there's also cultural issues where many developers will say, oh, okay, it's a machine generated test case. It's not real. I'm not going to spend my time on it, right? Ignoring the future value fixing it will provide when they, maybe don't have a test case and it's a million lines of code and buried in the middle of it, right? And so I think that it's both sides, right? The tools, the better the tools are and the better the test case reduction is, the more likely it gets fixed. As the world becomes more familiar with these techniques, I think people will take them more seriously. It's kind of similar to static analysis 10 years ago, or whenever the formative work came on the scenes, where a lot of people were saying, okay, well, yeah, it's a bug, but like, I don't believe it's important, right? And I think the world is evolving slowly towards that.
Right. Thank you. So if I can switch a bit gears towards Swift. So I have a question from Gavin Berman at Oracle. He's asking, were there any features that you thought of for Swift that didn't work out and were dropped? And if so, why? What were these features and why didn't they work?
So yes, tons of bad ideas were taken out of Swift. and tons of good ideas were added. Some middle of the road ideas, like, it's everywhere. In the case of Swift, a lot of this is public. And so if you go to the Swift evolution repository, you'll see that particularly in the Swift 2 timeframe, a lot of features were removed from the language because that was a time in Swift's design evolution that compatibility could be broken. And so I think if you go back, Swift used to have C-style for loops where you have a initial condition, a condition, and an increment. And that got removed because we can have for each loops and we can have smart iterators and things like that. The plus plus operator. So Swift used to have prefix plus plus and postfix plus plus and minus minus and things like this, and that got removed as not being worth it and causing confusion. There's a lot of things that go much deeper than that, and I encourage you to look at Swift evolution. The list of proposals, if you sort them by number, are roughly chronological, and so you get a very nice view of that. Swift also has a changelog that many people aren't aware of, and it goes way, way, way back before Swift 1.0. So back when it was very secret and very confidential, and you can see back when, we had pipe style closures where, Ruby style closures with pipes delimiting the arguments and all kinds of stuff like that. And so you can see a lot of how a real language came to be through its evolution and through iteration and change.
Oh, that's great to know. Yeah, I think that's a very nice resource to document the evolution and the history of the language. So, so I guess related to what you've been saying in terms of experimenting with new features and being agile in this way. So this is also something that I experimented a bit firsthand with the llvm. So we have several projects, including CLI, which we maintain in our research group, which are built on llvm. So thanks again for the fantastic work that enables many different projects. So we are spending, or actually at least at some point we're spending like a lot of time just updating our code base to be compatible with the latest LLVM, right? So I think some changes seem to be indeed necessary, right? And while others perhaps less so, lots of method name changes and things like that. But in general, I mean, I'm wondering, what are your views on backwards compatibility, on moving fast versus slow? Do you have stages in your projects in which you move a different?
Sure. So I mean, it's all about what are the objectives in this case. So the objective of LLVM starting out from the beginning was we need to build the world's best thing. And so we didn't want to be constrained by compatibility and get painted into a corner. Also, when you start talking about let's do version breaks at specific milestones, in the case of an open source project, you have to say who defines those milestones. And that can become controversial or political or whatever, right? And so LLVM has historically always said the C++ APIs are not stable. And then it has a subset of those APIs exposed as C, and those C APIs are either fully stable or pretty close to fully stable. And so the basic IR construction things you can use from the C APIs, for example. Now, the reason for that is both be able to move fast, be able to get to the best answer, be able to evolve and adapt to new changing requirements. But it's also because we want people to be incentivized to contribute things upstream. we actually want it to be expensive to maintain huge patches out of tree, because that encourages the XYZ target maintainer to actually upstream the changes they're doing versus just keeping them in a stable long-term evolution branch. And that's one of the things that I found interesting about the GCC community many years ago, which is the GPL compels you to release the code if you get the binary product that came out of all that kind of stuff, right? But it doesn't compel you to do two things. One is it doesn't compel you to write good code so that somebody would want to use it. It also doesn't compel you to contribute it to GCC, right? And so there's a social issue with the open source project where even though theoretically you can get at and look at the code and reproduce a binary, fine, it's not super useful in terms of propelling the health of the open source community over time. And so there's not any good answer to this, and llvm is intentionally a very permissive license, so people can take it and use it and do whatever they want. That's a good thing. But we do want to build the community and draw people back in. And so for you, Cristian, I would say, why not contribute CLI to the llvm project? Why not make it an official thing, right? And see, there you can, if you make it a sub-project, then you could get the benefit of a broader community, and you could also get out of some of that merge maintenance.
Right, that's true. And in fact, CLI has started like that, being part of the llvm tree, but I think we found it, coming from the academic side with fewer resources, we found it a bit difficult to maintain the pace, right? But yeah, perhaps now that CLI also has a larger community, this would be more doable.
Yeah, it's worth considering. llvm also recently moved to GitHub, and so with that, it now has a monorepo, and so that also makes the testing and the maintenance problems, the CI problems like that a little bit easier as well. So, I
mean, on the other hand, I must say I also noticed that recently llvm has started to evolve a bit more slowly, right? So from llvm 7 on, the kind of changes that we had to apply were actually quite small, while before that, I think they were quite dramatic in some.
Yeah, I mean, the other part of your question was about the natural evolution of a project over time. Right. The llvm community is getting a lot more conservative, and there's a lot of big companies building gigantic piles of technology on top of it, and there's a lot of reasons why people don't want it to change. It's not just you. That's actually a problem in my mind to a certain extent. I mean, it's good on one hand, and I think everybody appreciates that, but it's also a problem because llvm also has problems. It's a good thing, but it could be a great thing, and we shouldn't get stuck in the mode of not improving it and not making it better. And one of the challenges with having as many users is it just becomes very expensive / painful / demotivating to try to get big changes upstream that really improve the fundamentals. So that's something I'm watching out for and trying to encourage people to be more open-minded about as well.
Right. So I mean, there is also a question related to what you've been saying. So you partly answered it, but I still like to ask it. So it's from Ben Zorn from Microsoft Research, who's asking, what suggestions do you have in creating a vibrant and robust open source community around the software projects? So you mentioned a couple of things, but I wonder if you can more.
That's a great question. I think that most people completely underestimate the cost of building a community. There's a huge difference between, proprietary closed source software, open source, where you periodically publish a tarball, visible development where people can see patches as they go in, up to the point where you take patches, which is now much more common than it used to be. And then finally you get to the point of trying to build and foster a community, right? And these are all different levels of investment that I think it takes from a development team. And particularly when you start out, many projects start from kind of a center of gravity. So it's a company or a group of people that are working on a research group that are working on a thing. And they have specific ideas, the specific things that they're pushing, and then it kind of grows out from there, right? And so I think the biggest thing to understand is that is an expensive prospect in terms of time, in terms of energy. And it really requires the engineers, the developers, the contributors to really put time into other people.
Right.
right? And this is not just a management problem. This is a culture challenge where folks have to buy into that fundamentally. And if you follow the precedent of other communities and you can kind of cargo quote forward some of the practices, I think that can really help, because this has been done, and llvm is one of them, but there's many other successful open source communities. And there's a lot of infrastructure around and a lot of culture around these projects that is hard to get going from scratch. And so things like coding standards and the way patch review works and a lot of these kinds of things, GitHub, for example, is really great at providing a starting point for a lot of that, but there's still a long ways to go in terms of the full how we work together part of getting smart people across the world to collaborate.
Yeah, that's true. I fully agree with that. So I have a related question, somewhat related, from Martin Berger at the University of Sussex and also High Silicon. So he's asking, he says, most software in the processor design space is closed source and very expensive. Over what time frame do you expect those tools to be replaced by open software? And what open source business models do you expect to pay for their development and maintenance?
Yeah, so you're asking about the EDA hardware design part of the problem. So I'm focused on that right now. I don't have a crystal ball, so I can't say it's going to be 3 months. Pretty sure it's not going to be 3 years, 30 years, 300 years. So I don't know exactly what will happen. I know that there's a burgeoning compilers for hardware community, and there's a lot of really great projects, including Yosis and Verilator, and many of these tools. Open Road is a new project that's trying to pull together some of these communities. The problem with them all, from my perspective, is that they're all redundantly implementing the same stuff in many cases, and they're kind of fighting together. And so there isn't a center of gravity that's pulling the community together in that space. There's some stuff that we're working on now that may be announced in the next few weeks that may help with some of that, but it's a fairly inherently challenging problem, because you have a lot of great research projects, a lot of great open source tools that are solving individual subsets of the problem, but the subsets have small intersections in some cases. In some cases, they have large intersections, and we have people that are not collaborating because they're, one's written in Haskell and one's written in, whatever, and things like that. And so I don't know how to crack that, but until we do, I think that it's going to be fragmented. Now, you ask about proprietary tools. Proprietary tools are just as fragmented. I mean, even within one vendor, a lot of the tools are created through acquisitions. And so there isn't a lot of even internal consistency across one vendor's tools. And there's a huge opportunity to improve the space. So
thanks. So let me see. Right, so I have this question from John Wickerson at Imperial College London about LLVM. So why do you reckon LLVM has become so stratospherically popular? Is it for technical reasons, like being simpler or faster or more extensible than its competitors, or also for social reasons, like being advocated by influential people and organizations at the right time, or a bit of both?
I say both. I would also throw in license as some kind of contributor there. I don't think that there's any one answer. I think it's different things in different times. The move to GPL v3 was not the reason that some contributors moved to LLVM, but it definitely helped. So I think that I would say it's a combination of LLVM is useful, and so it is solving specific problems that people want. And when people want to do research, for example, in, you talk about CLI, for example, is a great tool in the space. You want to focus on the research problem that you care about, not about building all the infrastructure underneath it. And so I think that the most profound aspect of LLVM that has really helped move this space forward is the modularity. The fact that it is not a monolithic, it is a C compiler. Instead, it's a pile of libraries that can be sliced and diced and applied to different kinds of problems in different ways. And to me, I'm very happy when I see people do things I never even thought about or never even imagined, when you're surprised how something gets used. And that's really only possible through clean design, proper layering, correct interfaces, through a community and a structure that values that. Having a healthy open source community, to Ben's question, I think is also an important aspect of this as well, because then you get not just the one arrow through the technology that one organization cares about, but you start to get multiple different vectors going on where different people in different organizations are caring about different things, and that leads to it being more well-rounded. And so I think that it's a combination of all those things.
Right. So let me ask you a couple of questions about machine learning.
Sure.
So I have one question from Emmanuel Lima at University of Sao Paulo. So what do you think is the role of machine learning in compiler optimizations? Do you think that the probabilistic nature of ML is a deal breaker for using it in compilers?
Okay. So this is use of ML within a compiler. So
right.
Compilers are also useful for helping ML. But so my view on this is
that's the next question. Yes.
Oh, okay. So you may have noticed that compilers get described as these beautiful Platonic ideals of these algorithms that you can read about in a textbook. On the one hand, on the other hand, you go look at them and they're full of horrible heuristics and all kinds of grungy details that then make spec go fast or something. And so the classic example of this is the inliner, for example. The inlining heuristics are just completely nonsensical heuristics handwritten by somebody to achieve some goal, and it was good enough, they move on. Machine learning is a way better way to solve this problem. You can train across tons of data. You have large scale code bases you can train against and learn and generalize from. You can run experiments. There's a tremendous amount of data you can mine out of this. One of the challenges is that the existing compilers, llvm included, were never designed for ML integration. And so there's a lot of work that can be done to integrate ML techniques, including caching, offline analysis, and things like this, to integrate that into our compiler frameworks. But because the abstractions are wrong, it's really hard to do that outside a one-off research paper. And I don't think the probabilistic nature of that is necessarily a challenge. If you think about in like the depths of a register allocator, so llvm has a register allocator that can do live range splitting and spilling and rematerialization and all these different things. That inner loop of the register allocator is pulling a live range out of a set and just trying to decide what to do with it. Having a prediction algorithm say, oh yeah, we think it's better to go to split this, for example, would be completely sound. You could make it deterministic, and it probably would have a lot of value. I would not use machine learning to like answer alias queries, for example. That might be a bad idea. But right. It could be interesting to get a limit on things. So I think there's a lot of room for that. I think that the existing frameworks are not perfectly well set up for that, but there's definitely a lot of work to be done there.
That's great. So let me ask then the kind of symmetrical question. So also from Ben Zorn at Microsoft Research. So what are the major changes to the software development process that you see being caused by the wide adoption of ML and AI in applications? And I think focusing specifically on compilers would be quite interesting.
Yeah, so I think that we're very early in ML pervading software development. I think that what I see is, people are treating ML algorithms, most people are treating them as a function, right? I can use a model to train a cat detector. Now I have a cat detector function, I shove in an image and I get back a prediction, right? Or I treat it as a function that turns audio into written words or things like this. They're basically functions. I think that the thing I'm most interested in is when you start blurring the line between imperative programming, object-oriented programming, functional programming, and ML techniques. And I think that when you start to do that, what you end up getting is ML as merely another programming paradigm. And it's a programming paradigm that's really, really, really good at solving certain classes of problems. I would not write a bootloader using machine learning, for example. So there are classes of problems it's not very good at. But it's a tremendously useful way to solve problems in the domain that most humans live in. And so I think that it should be just part of the toolbox. And the more we can break down the tooling gaps, the infrastructure gaps, the language gaps, and make it integrated with the normal application flow, the better we'll be. This is the idea of the Swift for TensorFlow project, if you're familiar with that.
Thanks. So let me also, because I was taking a closer look at the Slack channel, so let me also mention a couple of points that the audience commented on. So Ben Zorn said, great point about ML integration of compilers. This is happening across many different systems designs, operating systems, databases, compilers, and so on. And also a comment from John Rogier at the University of Utah. My total favorite quotation, real compiler is different from the textbook, is GVN, which seems pretty lame when you first read about it, but turns out to be sort of a massive hammer in practice.
I mean, to me, one of my favorite compiler optimizations is just canonicalization, right? That dumping, like in schema, and that dumping, that toolbox where you just dump special cases into, and it just makes things better.
Right.
and I admit it's a love-hate relationship, but it's one of the most powerful and most important in practice.
True. So I'm also aware that we are unfortunately past our our 30 minutes, but I think we can go over by a few minutes, and there are actually tons of questions. I think that unfortunately
go for it. I have time
on Slack. So let me perhaps end with this question about about the future, right? More future-looking question from Ishan Gard at Cornell University, who's asking, what, in your opinion, are the biggest problems that current generation compiled languages need to tackle for the future?
Okay, so we're scoping into current generation compiled languages. Okay, so I can answer that in a couple of different ways. I think that partially my fault, but I think that many of the modern compiled languages, in which I would include Swift, Rust, a bunch of that kind of 2010 and later kind of languages, have forgotten and are rediscovering the value of high-level IRs. Right, this is something the Fortran community has known for decades. Many other functional programming communities have known about progressive lowering and things like this. And I think that having a high-level IR, a language-specific IR for doing much more flexible transformations is very useful. Clang, I'm on the record of complaining about the fact that Clang does not have one of these, and this causes lots of problems in the C++ community and in the llvm Clang community as well. And so I think that that is a big question. Now, when you start to build those, there's a huge tooling question. And this is a tooling question that the MLIR project really tackled by saying, look, building these IRs is a lot of work. You need to build a lot of infrastructure to do this. And again, it comes down to that research question where you're saying, hey, I want to achieve a thing. And the thing is an optimizer for my language. Why am I writing an instruction class? Why am I writing a people optimizer, right? Why am I writing, or why am I not writing a declarative pattern rewrite system? Why am I having to reinvent testing for this thing? Why am I having to do all this kind of make work? And I think this is something that MLIR is really useful for, and I'm very happy to see it being adopted in a number of domains, including hardware design now. That's really just, it's nice to be able to pick up high quality infrastructure and be able to build cool things out of it. So I think that space has not been explored as deeply as it should, merely because the infra has not been good enough. And as that technology will diffuse through the compiler design community, I think that we'll start to see new and interesting things. So,
right, yeah. So thanks again for all the insights that you provided, and unfortunately we do need to wrap up because I'm told that there is another Ask Me Anything session that has to start. And as I said, there are actually quite a number of other questions on the Slack channel, so you might want to take a look later on.
Sure. Well, maybe we can do this again next year.
Right. So thanks again
for
your time, and also for all the fantastic contributions to the community.
Oh, sure. Well, thank you for having me. And from all of us Americans, happy Juneteenth. So
see you, Chris.
Talk to you later.
Bye-bye.